Is Michail Basios. I finished recently my PhD at University College London, and I am the CTO of Turing Intelligence Technology, a startup that spun out from UCL. In this presentation, I'll talk about how we can automatically optimize the performance of applications by better selecting and tuning the data structures that those applications are using. This talk is a combination of the research that I did during my PhD, as well as the product that we are currently, one of the products that we're currently building in our platform. So, a very quick intro about myself and our team. So, we are a group of PhD students from UCL that were doing research in automatic code optimization. And we decided after our PhD to focus and build a startup that focuses on how we can automatically generate more clever version, more optimized version of code by using artificial intelligence and machine learning techniques, and more specifically, search-based software engineering techniques. In our company, we have been building two products. One is Artemis, the one that we are going to present today, and the other one is EVML, another product that we focus on automatically generating efficient machine learning models. So a lot of developers, and I'm sure a lot of people in the audience are familiar with Donald Knuth's advice that we should forget about small efficiencies in the code, say 97% of the time. Premature optimization is the root of all evil. Indeed, it seems that a lot of developers are following this advice, but they seem to neglect also the critical 3%. And that's also usually happens because the focus is mainly on the user requirements. So as this meme is saying here, is like there are always coming new and new requirements, so you always don't have time for optimization. And as a result, a lot of code can be deployed and used which is unoptimized. And as we have noticed on a lot of applications that we have been scanning and looking at, it's not only the pre-optimization that Donald Knuth says, it's a lot of inefficiencies in a lot of places in the code, and that also one of the reasons that happens is that the machines nowadays and the power that developers and the machines that developers have access to are becoming better and better and bigger. So why should we bother when the machine is already very powerful sometimes? So as a result, you neglect optimization. But as we will show in this talk, and with the power of artificial intelligence and nice tools, optimization can be very beneficial and easy to be applied. And we want to avoid problems that we see in the applications, like very slow application or application that have a lot of memory usage, or mobile apps that use incredible amount of energy consumption. So our focus is to solve this kind of problem by automatically optimizing the performance of applications. Data structure selection and optimization process. So data structure selection and optimization process is very critical for the performance of an application. As we know, most of us are experienced when we are applying for jobs. Usually, one of the most questions are coming around data structure understanding. And even though a lot of developers know the different variations of data structures, if you're taking programming language like Java, C# or others, for each data structure, you also have a lot of different implementation. And I think most of the times, developers may neglect to use the various implementation or may not be aware to use the various implementation. And this selection, which sometimes may be straightforward, may sometimes lead to usage of data structures that are not efficient for a particular problem. Usually developers may just choose the most popular data structures that are very well and very performant on more generic use cases. For example, in Java array list, if when we analyze the code, that we saw that our array list is used much more than a linked list. Now, how a data structure can affect the performance, we can see in this motivating example from a function that we extracted automatically from Guava library. So what we can see here, this code is using a data structure in line 3, which is an array list, and also there is also a size that can be defined by the developer, but in this case it's not used. Now, array list, when you allocate, it will consume 10. The memory consumption is going to be 10 in this case, because it will allocate 10 slots to us. That is the default size of array list when you define. But if this function is called like millions of times, then every time you will allocate these 10 slots, so you may consume a lot of memory. The other part, which this code will work absolutely fine if instead of array list we can use linked list. So that is an example of how with very simple code changes we can potentially benefit from performance. And more specifically, usually when people select data structures, usually there's a trade-off between time and memory consumption. Usually either you'll choose a data structure that you allocate more memory, but you can have, for example, direct access, or you don't need to copy many times the memory, so it's more efficient in time. But it can be also the case that you may choose a data structure that for a particular use case you consume less memory, but it's quite slow. The ability to interchange between those data structures automatically in a very big code base, that is what we are trying to achieve at this with our tool. And it's not only the data structures that usually are coming with a default library of a programming language like Java, but there are also other implementations of data structures that are very specific to use cases. And we have seen that a lot of developers do not use those specific data structures. Like in this example, for Java especially, there are some other libraries like Eclipse Collection that they can provide a faster implementation when your data structure is focusing on primitive types, for example, where the default data structure in Java, until the latest version, they didn't support primitive type, and you need to use another, like streams, for example. But there may be other implementation that it would be very nice developers to use, but they may not be spending the time to investigate. And they are also those kind of data structures. Sometimes they may follow already the interfaces of a Java main library, so they may also be easily integrated and interchanged. So, in our paper, the paper which is called Darwinian Data Structure Selection, and it was published in 2018 in FSC, we applied our tool which automatically extracts data structures from different code bases and changes the code to use more efficient data structure using an optimization technique. We managed to apply our tool in 43 projects for that paper, and we have applied, and I will show you later the tool that we can apply it in more projects. We show that we automatically optimized a lot of metrics, including execution time, 5% on median, 10% memory consumption, 5% CPU. Those results are understating the real power of this tool, because what happens is that those projects, we apply them on the default test suites that those projects come with, because as we realized, most of those projects don't come with a performance test suite. And by a performance test suite, I mean like for applications to really optimize them, you need a realistic behavior of the application. And having that realistic behavior of application can really show how you can change data structure and how that can impact the performance of code. Like in some projects where we had better performance test suite, we saw that the performance improvement could be like in some like 20%, 30%, memory consumption 23.5%, for example, in the Xalan XML tool, and even popular Google JSON and other projects. But how do we do that? So practically, what Artemis does is that it monitors when an engineer writes their code and they push that in the repo. Artemis monitors all those pull requests, like as a continuous integration service. When a pull request happens, Artemis will go over the code. It will detect the data structures as well as the functions that are the hottest functions. It will detect the data structures. It will run an optimization service, optimization algorithm on the backend. It will test that it will run the test suites that the program is coming. It will evaluate the final performance, and it will give different variations of the code as pull requests depending on the optimization criteria. For example, Artemis is optimizing both execution time, memory consumption, and CPU usage. This is a multi-objective optimization process. Thus, it will generate a lot of different variations of code, different solutions, which are optimized for the specific metrics. So it will give in the end all the non-dominant solution, and it will suggest the best for execution time, the best for memory consumption, the best for CPU usage. This allows developers to have different versions of their application optimized for the particular hardware potentially that they want to deploy. For example, developers may want a version that has less memory consumption because they may want to deploy that in an older mobile device, or they want a version that optimizes the energy consumption because again they want to deploy it in a mobile device. So how do we do it? So Artemis first does static analysis on the code, extracts all the data structure as well as their parameters, and exposes them as a list of optimizable, tunable parameters. So then we use search-based techniques, which comes from an area of research that we are doing at the University of College London, which uses genetic algorithms and other techniques to find the best combination of those parameters. We define what we call the Darwinian data structure. Is any data structure that has a kind of interface and comes with a set of implementation. This definition comes, this is a simple definition that we are providing in this, and we are applying it in data structure, but this can be applied on every other similar type of problem, where you may have, for example, a function that you have similar overloaded function following overloading the same parent function. Thus, those functions can be interchangeable. Those, we can consider them as Darwinian data structures. This meaning that allows our tool to be easily extendable. The architecture of Artemis starts as follows. Like initially, the Artemis just needs as input a project, and we assume that the project has a build system, either Maven or Grundle or Bazel, and also we assume that the project comes with some test suite. If the project comes with a performance test suite, that's even better. Now, Initially, the preprocessor scans the program source code and uses an AST traversal algorithm to extract the data structure as well as the parameters. We predefine the set of data structures that we will expose from a program. We already have built a set of interchangeable data structures, and the users of Artemis can also define what they want to optimize in the program in the same way that we are defining. Now, the preprocessor and the AST traversal generate a template source code, which is practically a version of the code where you have, template where you have the data structure replaced by templates. And then all those data structures are converted to a big array of optimizable parameters. Then we use that big array as an input to our multi-objective genetic algorithm, and we run it for multiple iterations. So practically, you take that big array, you generate from that solution the code, which we call the mutant version of the program. We evaluate it, and we continue generating newer and newer solutions. So this algorithm may run for some iterations. If this is a genetic algorithm, so usually you may run it for 30 iterations for each time 10 different solutions. And when this process finishes, at the end, we'll have all the versions of the code which have the different, which are optimized for the different optimization objective. When we So what is the improvement that Artemis provides for each measure? So when we tried Artemis on popular GitHub projects, on the test cases of those, we measured, we had improvement on execution time 5%, on memory consumption 10%, and CPU usage as well 5%. When we tried also Artemis on Da Capo benchmark, we had a kind of similar behavior, and we improved FOP around 10% on execution time, and here we saw that we had better improvement on memory. Like for Xalan, for example, we had around 20% improvement. And we did proper, of course, for the experiments that we did, we took into consideration the warm-up of JVM. We did a lot of iterations, like we ran each program 30 times, and we also took average and median values, so we could be sure that the optimization that we were and the variation that we were introducing to the code wasn't just a random. We saw that Artemis, our goal was to make as simple as possible changes between data structures, and we saw that for a lot of solutions, Artemis sometimes would change. Usually from hash map, it would prefer linked hash map. Other time, it would prefer linked list would convert to array list, and also the opposite. Like we see as well array list to linked list. I guess those array list to linked list, most of the use cases, I think there were for the memory consumption, as we see, of the 86 data structure. In general, Artemis extracted for all the 40 projects around 12 data structure in each of them. And when we changed, usually the solution would have 5 data structure different from the original one. The cost of Artemis, when compared to the cost of software engineering, it's much cheaper. We used cloud resources to run all our optimizations, and we have now Artemis as a service that can run on the cloud. So whenever you make a pull request, we will start a service on the cloud that will run the different versions, and then we will generate the latest one. Usually the average optimization process for the project, it was around 3 hours. But Artemis, as you don't need to run it on every pull request. Actually, you can run Artemis maybe when you have quite a lot of changes in your code. So you can run Artemis every 1 month or every 1 week, depending on how fast people are making changes in it. And Artemis not only changes the code, as we said, but we decide to give it as a pull request because we want the developers to see the changes that were happening. And usually the changes are less than 10 lines of code, so that they can easily review and accept. So what makes this tool cool is that it automatically identifies and tunes the data structure and its parameters, like the tunable parameters that some data structure functions, they can also be exposed as optimizable parameters. And we can better choose, let the optimization algorithm choose also, better default variables for specific data structures depending on the behavior of the program. It's quite easy adaptable, like we have applied Artemis now on new APIs and also on new languages. It is multi-objective. It means that it doesn't optimize for only one objective, but it can allow the users to have multiple variations of their program. It can scale on the cloud, and it can integrate very easily in a nice continuous integration pipeline. We are working, and we have been working as well on some improvement. Like there is a very big need of performance test suites, so we are working on how we can automatically generate performance test suites for Android application, for example, because this is one of the biggest problems in our research as well, the lack of performance benchmarks. We are integrating more rewriting rules to gain further optimization and to extract more features from code that can be optimized. Like this Artemis can take, if there are other tools that can give more context on where Artemis should look to extract optimizable parameters, then Artemis can potentially provide even better optimization results. And we are focusing also now on mobile application, so we want to make them consume less energy. We are providing Artemis as a command line tool, but as well as a web service and as well as a continuous integration service. Now I will show a live demo, which I have the video here of how Artemis looks in different cases. So the first case is Artemis. We applied this in let me see. So Google Java format, it's a very well used popular plugin for formatting the source code. So in this case, the way we use Artemis is Artemis, we put the URL that we want. In this case, it's going to be Google Java format. And we have a predefined list of data structure. And we see that in this case, Artemis scanned the code and found 31 data structures. After we found those data structures, the first thing we need to do is to regenerate the code and evaluate the performance of the default Google Java format when you run it. So in the first time we compiled, as we can see here, Maven package, and the second time we are running the tests of this program. Now, as we see, let me see here, as we see, we measure execution time, CPU usage, memory consumption. So this is the total cycles, which is 85 in this case for the original solution. Now Artemis, what did we introduced a new solution, like automatically generated a new solution which has 17 changes. If you see, like array list was converted to linked list in different places. All those changes now now we generate a new version of the code, we compile it again, we test it again, and we measure the performance. This process is the start of the optimization process. In the beginning, the performance may not be very big on the solution that we generate, but while the algorithm is running, more and more better solutions are generated. For example, here we generated a new solution with 15 changes happen. This was for Google Java format that I think we let it run, and it generated various solutions, and some of the solutions were better both in execution time and memory consumption. Another application of Artemis is on Android phones, and in this video we show how we again take a popular GitHub open source project from F-Droid, which is a game that people can play on Android. So again, the same thing. We extract 20 data structure from Artemis extracts 20 data structure from this tool. It executes the tool. It compiles the tool. It runs the test, and then it executes a benchmark of this tool. So this is a random benchmark that we created about this tool, and then we measure the performance of this variation. This is the original solution. Then what happens? Artemis generates a new solution again. So we change a new solution where 10 data structures were changed automatically. And now we compile and we test. Now we run the new version with the changed data structures, and then we will measure execution time, CPU usage, and memory consumption of this tool. And of course, the optimization, again, the more it runs, the better solution it generates, and in the end you have the version of the source code as well as a report with the changes and the performance improvement that was achieved. And the last version, quickly, it is Artemis. We have a first version of our web interface where people can sign as a platform, and they can put through our dashboard the code that they want to optimize. In this case, another GitHub project, Joda Time. Again, they start an optimization process. They put and Artemis, in this case, starts on the background. Before it was Artemis as a library. So the background, we run a lot of processes, and each variation of this process gives back a solution which is optimized for the different metrics that we have. Yep. That was a kind of introduction of Artemis. Any questions? Thank you.
Awesome. Thank you so much, Michael, for the amazing presentation. I think it was really interesting and a great example of how research can be combined with engineering to deliver some extremely promising results, and a great continuation of some of the work that Eiko has also mentioned during her talk. So while we are still waiting for the questions pop up, if anyone has any, I'm gonna go ahead and ask my own question. So I'm curious, most of the optimizations that you mentioned are applied at the source level. So basically we change the source code and then we try something and then we get the data. So the first question would be, have you tried doing something like that in JIT? Because JIT usually has a lot of speculative optimizations, like for example, when it removes multiple implementations of interfaces based on number of actual classes, and also some of the optimizations that I've discussed with the Dmitry, for example, when you can have a use case that would benefit from a data structure that is optimized for that particular use case, but you can always change the decision dynamically based on how your data changes. So have you tried something like that?
Yeah, thanks, Taras. Yeah, that's a very good suggestion. We haven't gone into this level right now. We are trying to build a generic optimization framework that you can map different programming languages, actually. Like in the paper, we also have some use cases in C++. So we wanted with this tool to make more popular search-based software engineering approach, and people to be able to provide more and more optimization while they are using our tool. Like using this version, for example, like Artemis could be easily extended if you have better profiling, for example. So the Amazon profiler would be very useful to help us guide the search, because the search of where you should optimize your code is the first thing, and then the second thing is what are the alternative implementation of a particular data structure in this case, but any library or API that we may be looking. So definitely, like if we have some more statistics that we know that JIT can give you better optimization for particular data structure or for particular pieces of code, then we can put that so Artemis can make those changes in the source code, and then JIT can take advantage of those. But yeah, I think we can look that in the future in more detail.
Awesome, thank you. I really want to continue this discussion. Fortunately, you're gonna be part of the panel discussion, so I hope we can pick up this conversation, because we are a little bit behind the schedule. So we're gonna just stop for a 1 minute break to give Stefana and Giovanni a chance to prepare for a further talk, which is again goes into it basically continues this discussion and is named from manual performance testing to automated performance optimization. So see you in a minute.